Welcome to homework.
We are asked to use the formula for the Bell numbers to find the number of different equivalence relations on a set with n elements, where n is a positive integer not exceeding 10. So first of all, start off with n equals 1. So in this case, we have the initial condition well, I guess really to be accurate, we can start with n equals 0. So this is a set with 0 elements. This is the empty set. And by definition, we have that the initial value p0 is 1. Now, consider when n equals 1. So in this case, we have that P1 will denote the number of different equivalence relations on a set with 1 elements, and P1 is given by the recurrence relation P1 equals the sum from j equals 0 to 0. So this is simply with j equals 0 of C0, 0, times P of 1 minus 0 minus 1, which is P of 0, so we have 0 choose 0 is simply going to be 1. P0 is 1, so this is 1 times 1, which is 1. Now consider n equals 2, the number of equivalence relations of a set with 2 elements. From our formula, this is going to be P of 2 is sum from j equals 0 to 1 of C of n minus 1j. So this is going to be C of 1, 0, and then P of 2 minus 0 minus 1 is P of 1, plus, and then this is going to be C of 2, 1, 1, 1, I mean, and 2 minus 1 minus 1 is 0, so P of 0, which will give us, well, 1 choose 0 is 1, times P of 1 was 1, plus 1 choose 1 is 1, times P of 0 is 1, so this is going to be 2. For n equals 3, we have that P of 3 is going to be C of 2, 0, P 2, plus C of 2, 1, or my mistake, it should be C of 2, 0, and then P of 2, okay, C of 2, 1, P of 1, plus C of 2, 2, P of 0. And this comes out to be, well, 2 choose 0 is simply 1, so this is 1 times P of 2 we determined was 2, plus 2 choose 1, this is going to be 2 factorial over 1 this is just 2, times p of 1, we determined was 1, plus, and then 2 choose 2 is 1, times p of 0 is 1, so this is 2 plus 1, which is 5. Now, if n is equal to 4, we have that p4 is equal to c3 choose 0, p3 plus c of 3, 1, p2 plus c of 3, 2, p1 plus c of 3, 1, c of 3, 3, p0. This is going to be equal to 3 choose 0 is 1, p3 was 5, plus 3 choose 1 is 3. Well, no, 3 choose 1 is, yeah, it's 3. And p of 2 is 1. No, actually, p of 2 is 2. 3 times 2. And 3 choose 2 is 3. And p of 1 was 1. Plus 3 choose 3 is 1. And p of 0 was 1. So we get 5 plus 6 is 11. Plus 3 is 14. Plus 1 is 15. I'm just going to speed up the process here for the rest of these. So we have that for n equals 5, well, p of 5 is going to be c of 4, 0. This is simply 1 times p of 4, which we determined was 15, plus c of 4, 1, which is 4, times p of 3, which is 3, plus c of 4, 2. This is going to be c of 4 factorial, 2 factorial squared. So we have 4 times 3 over 6 times p of 2, which is 2, this should actually be 5, not 3. My mistake. And then we have 4 choose 3, which is 4, times p of 1, which is 1, and plus 4 choose 4, which is 1, times p of 0, which is 1. So we get 15 plus 20, so 35, plus 12, 47, plus 4, 51, plus 1 is 52. So you see that as these get greater and greater, they become harder to calculate. And so we have that for n equals 6, p of 6 is going to be 203. If n is equal to 7, p of 7 is 877. If n is equal to 8, p of 8 is going to be 4,140. If n is 9, p of 9 is 21,147. And if n's 10, this would take a very long time to calculate. P of 10 is 115,975. So for this function, it would seem that an asymptotic approximation would be quite useful for these large n.